Okay, those chemistry students, homework video number 3, potential energy diagrams, energy of position. We basically need to identify the basic parts of these diagrams, which is actually going to happen in the next video. So there's 2 videos for potential energy diagrams. We're going to break them up, and let's start, and then after you're done with both, we'll have lots of stuff for you to do. Chemical reactions occur, but can I graph them? Yes, and we are going to revisit some old terms that we know. Endothermic, adding heat. Exothermic, heat leaving the reaction. It's going to work out just the same way, but they're going to look different when I make my potential energy diagrams. So first, the potential energy diagrams, I have to break bonds and form bonds. So, as we start, we'll do reactants on the left like before, products on the right like before. Okay? Breaking and forming bonds. Heat of reaction, delta H, is the amount of heat energy lost or gained throughout the reaction. The delta H refers to enthalpy. We'll have a full video, I believe in number 7, video number 7 will be enthalpy. But here's a good way to remember it right now. Delta H has an H in it. There's another word for video 8, it's called entropy. We can't get the two confused. They sound very much alike. Entropy, enthalpy. Entropy, enthalpy. Very easy to confuse the two. The best way to keep them separated is an H in enthalpy, so that is H. To find delta H, I always subtract the delta H of the reactants, the heat of the reactants minus, let me rephrase, stop. I'm going to take the heat of the products, subtract the heat of the reactants from it. I need to do it specifically in that order because the positive and minus of the delta H makes a difference, and we're about to find out why. So, 2 types of reactions. First one, exothermic. In an exothermic reaction, the value of delta H is negative. Muy importante. The other way to figure this out is I have my reactants on my equation. My products have energy on the right-hand side. So I could look at this chemical equation and see that I put 2 things together and energy is a product or released. So energy being released is very much the definition that we already know as far as exothermic. It is exiting the system. Okay? There's one other kind of reaction, of course, and that would be endothermic. Endothermic, the delta H is very much positive. Okay? And I can see that in my equation because now energy is being added to the system as a reactant. I need to add energy to make it go. If I'm adding energy to the system, it is endothermic, very much in line with our previous learnings. Baking is a good example. I must supply heat to get the cake to bake. Endothermic. Table I, reference table of delta H values. There is a whole slew of these guys. Can you see this, or is there not enough light? I need to add light. Can you see this? Can you see it now? Can you see it now? Delta I. There's a whole list of these chemical reactions and their delta H values. I'll do number 2. You have to do 1 and 3 for full credit for your homework. I'm looking for N2 plus 3H2. I'm just going to scroll down looking for my N's. There are a few of them. I find it right here in the middle. N2 plus 3H2 goes to 2NH3 gas. Very specific. Everything lines up. In these examples, there are just gases. We will find that there's liquids in here and some aqueous solutions in here. You need to be very careful and very mindful that you're finding the exact right one. Now, I find number 2. It's here. The number is, delta H is negative 91.8. Because it's negative, I know that it is exothermic. We just learned that on the last page, and we just did it. The one piece that it doesn't talk about in the notes is, what if I were to do this? 2NH3 gas goes to N2 gas plus 3H2 gas. Well, guess what? This number would be the same, but now delta H, instead of being negative, would be positive 91.8. So if I go the other way, I'll be endothermic. if I go backwards. And that part isn't really in the notes, but we'll throw it in there right now, just so we know. Okay? The forward reaction. Oh, look at this, forward reverse reactions. Going from left to right. So everything we've ever known about reactions is true. That's how it goes. We just call that the forward reaction now. Some of these reactions are reversible, we could say. And that goes backwards, like reverse, just how it sounds. But now, the C and the D, when I'm going in the reverse direction, these actually become my reactants. So we have to pay attention now of which way the arrow is pointing to tell me which way is my my reactant and my product. It isn't just so much the left-hand side now. Okay. Activation energy is specifically the amount of energy I need to get started or to get to this thing called the activated complex. Next notes, I'll define exactly what the activated complex is, but I'll show you a little picture on this next slide. Here's an example of a potential energy diagram. We'll find that they always look like this to some degree. The other different one you could find is it starts low and ends high. In the next notes packet, we're going to discuss how that's different in the next set of notes. This particular one just wants to talk about, okay, here's my H of reactants here. Here's my H of products here, my potential energy. This piece is that activated complex. And what I'm very much concerned about is how much energy I need to get from here to here. Because that is how much energy I need to get the reaction to go. And if you think about it this way, if I had a little shopping cart down here, would I have to put in energy to get it to go up the hill? Well, absolutely. And then, if I was already at the top of the hill with my little shopping cart, would I have to put in energy to get it to go down? Well, actually not really. I could just let go. I wouldn't actually have to push. I could just let go and off it goes. So this is the amount of energy that I'm really looking for, and this energy is called the activation energy. That being said, we can start talking about what a catalyst really does. A catalyst is, let's do the notes piece. Right? The catalyst shortens the reaction time needed because the activated complex is lower. So the activation energy gets lowered. And it specifically provides an alternate pathway. And if I were to add a catalyst to this particular reaction, the new diagram would look like this. Now, the H of R never changes and the H of P never change. The products and the reactants never change. But the amount of energy I need now did change, and it takes less energy, hence it's faster. That's how that works. Let me scroll down, make sure there isn't any pieces you're missing, and we're good. So this notes video is done. There is no practice video until we get through the next set of notes that further gets into potential energy diagrams, but we got the basics now, okay? So good luck, watch the next video, and then we will have lots to do. See ya.